I will travel where no man has dared to go.
The accepted laws of physics break down.
Boundary between the known universe and a place beyond the reach of science.
Ahoy hoy, Physics 2 students. Interesting little fact. Until Alexander Graham Bell created the telephone, hello was not actually the common greeting. And if Thomas Edison would have gotten his way, everyone would have responded on the phone with the greeting of ahoy hoy.
The new number is...
I don't know which one's better. But anyway, let's get to the first physics problem from the homework of Fluid Dynamics Part 2. We're talking about a jet airplane in level flight. So we have it right here. A jet airplane in level flight has a mass of 8.63 times 10 to the 4th kilograms. And the two wings have an estimated total area of 93 meters squared. What is the pressure difference between the lower and upper surfaces of the wing? And then if the speed of the air under the wings is 231 meters per second, what is the speed of the air over the wings? Assume air has a density of 1.29 kilograms per cubic meter. So let's get started, shall we? Ah, yes. Alright. So the first thing we have to think about here is what is going on in this actual situation. Alright, so let's actually first think about what's going on with the wing. Alright. So if we think about a wing and how it's shaped, I'm going to draw an aerodynamic wing here. That's a horrible drawing of it, but anyway, we'll know. The wing is bent here, so the air will flow further or quicker in this manner. Meaning that, so if we looked at airflow, we would have a much greater amount of drag up here as the actual fluid has to go around further. And as I said before in class, the way to tackle any sort of problem in fluid dynamics is to think of is it about a fluid moving through an object or an object moving through a fluid? In this case, we have an object that is moving through the fluid. So we will see that it should be a much difference. So once again, the conservation of matter says that this will have to make sure there's no gap there. So this fluid will have to move even quicker than this fluid does because it's going around a different amount of area. So when that happens, if we know the velocity goes up, then once again there is a lower pressure right here. And so let's get started on this actual problem. So right away we want to realize that we have, because this is a plane, okay, and it's in a direct straight flight this way, it means that our forces are balanced. So it means our force of gravity that is pulling us down, okay, has to equal to, if you will, the pressure differential that's actually allowing us to stay up and be matched. So one thing we'll start doing right away, oops, let me go ahead and clear this board, is we're going to think about, alright, so if that's a true statement, so I will say, well, the force of gravity then is equal to my mass times gravity, and that equals a force. In this case, we also know that that's equal to as well the pressure times area. Okay, so I can rearrange the equation to equal out that if I want to solve for the pressure, well, pressure is going to be equal to my mass times gravity divided by the area. And that's all it is. It's that simple. So all I'm going to do in this equation is going to set it up for 8 that's an 8.63 times 10 to the 4th, because that's what they told me was the actual mass of the plane. Big boy. Big ol' boy. Okay, and I'm going to multiply that times, of course, 9.8 meters per second squared. Then I'm just going to go ahead and divide that by the area itself. And the area they told me is 93 So when I go ahead and I punch it into the calculator, this one simply shows me that I should get a pressure, or in this case, it's a pressure differential of 990 pascals. Interestingly enough, the pressure times area is also PA there. Making any connections. So that's how you solve for that first part. Okay, it's not too complex. It's really that simple. And this is actually giving you, it's not just pressure, that's giving you, because we know the area and how it has to move around, we can say that we're going to have an area difference. So this is actually a pressure differential. So it's a delta P, which is also, then we'd say it's, you know, my pressure over top minus my pressure on the bottom. So I should say my pressure on the bottom minus my pressure on the top, because the pressure differential is going to be there, and should be less pressure on the top. So okay, now we have that one solved. Okay, once again, this just tells us the pressure around the wing, the difference between the two pressures, based on the area that we have. Alright. So now, the next thing we're going to do is it asks us to find the velocity. So it gave us all our information before. We know, once again, we have a delta P, okay, from this last problem, equal to 990, or 9,090 pascals. We have a, let's see, what else did they give us that we'll need? They tell us in the problem that we have a air density that is at 1.29 kilograms per cubic meter. Nice, no conversion. And then also that we have a velocity right on the bottom. So the velocity under the bottom of the wing is equal to 231 meters per second. Now, based on what we know when we solve, we know that in order for that plane to stay afloat, we know that the velocity on the top must be greater than the velocity on the bottom. Right, because that's what's giving us a pressure differential and allows us to have a force pushing up. So the equation I'm going to look at actually Bernoulli's equation. And his equation, once again, that we're going to be really interested in is the one he derived, which is just the P1 plus the 1/2 rho V1 squared. Now, I'm going to leave out the gravitational potential energy here because what we're calculating, there really is going to be no massive difference, right, in the actual the potential. We're taking it from like a, if you will, the middle of the wing. So I can leave out that gravitational potential difference. So I can just move it on to this and say that it's equal to P2 plus 1/2 rho V1, I'm sorry, V2 squared. So that's our velocity at the top. So if I rearrange this equation again, I'm going to take, first thing I'll do is I will subtract both sides by P2, and that'll give me P1 minus P2. So that's really, if you think about before, that's our delta P. So I have my delta P. Okay. Multiply both sides by 2, and that'll cancel out, so far I'll cancel out this, and then multiply both sides by 2, and it cancels out this, so I'm going to have a 2, right, times delta P, because it cancels it out here for that part, but here it comes over. And let's see, I need to get rid of a rho, so I'm going to divide both sides by my rho, and that still leaves a rho to be divided out here. Okay, and then I just go ahead and I still have that V1 from the original, so plus the V1 squared is equal to, And let's see, we have v2, but I don't want the v answer to be squared, so I'm going to go ahead and square root this whole bad boy. So now when I punch everything into my calculator, I should get an answer that's around, let's see, I have 200, why do I keep doing that? 231 squared. This is what happens when you don't take any breaks from work. Alright. Plus the 2 times my change in pressure. Okay. Divided by the density of the air, which is 1.29. And of course that, if I just did it in that standard form, would give me a v squared, but I don't want v squared. I want actually v. So I'm going to go ahead and do the square root of that. And when I punch it all in my calculator and get through with it, you should get 260 meters per second. And let's see, check for comprehension. Yep, this is a smaller number, right? So the air is moving faster over the wing on the top, which means there's a pressure differential, which means that my plane has a force pushing up on it that counterbalances the mass times gravity. So this plane flies, and no one is screaming and going down. So, hope this one helped. Thanks so much. Bye-bye.